What's happening, Webster? This is 8th grade science, goal 5, wave energy. What we're looking at in this goal is that you will be able to recognize sources of electromagnetic energy and how this energy exists in a range of wavelengths and energy levels. In order to do that, you're going to need to understand which section of the EM spectrum allows vision, recognize differences in wavelength and energy within the visible light spectrum, and how they result in differences of color, and recognize what is a source of light, and in turn, what is a receiver. Okay, so if you're going above and beyond that, you're able to apply your understanding of wave properties to the understanding of the electromagnetic spectrum. So here we go. Electromagnetic spectrum. Well, that is a word that we don't use in our conversation very regularly, and if you do, then props to you, because I mean, you just don't use it. I mean, how is your electromagnetic spectrum going? It just doesn't work. Examples of electromagnetic waves are all around us. Sunlight, which includes all of these waves come from the sun. And these waves include radio, infrared, visible light, ultraviolet, television, X-rays, gamma rays. All of these rays could be hitting you right now, although some of them are in very small doses or some are not even at all. The part of the EM spectrum that we can see is the visible light spectrum. All of the others are out of our range of vision, just like some sounds are out of our frequency. All of the other waves are out of our range of vision, so we just see the visible light spectrum. We can't see X-rays, gamma rays, although it might be cool. So we see the visible light section. How fast are these waves? I mean, kind of ridiculous fast. 300 million meters in 1 second. I mean, that's about, and to put it in miles per hour, that's 186,000 miles in 1 second. Whoop! 1 second. I mean, that's like 7 times around the Earth in 1 second. Imagine how fast that is. Okay, so light from the sun reaches the Earth in 8 minutes. That means the sun that reaches us is already 8 minutes old. It's like we're getting light from the past, you know? And that means that when we look at the sun, we're looking at an old image. That means if the sun blew up, we wouldn't know it for 8 minutes. Okay, anyway. So that's how fast these waves travel. Ridiculous fast. Light is a wave, and it's not a wave. What? There are times where it's easier to understand light as a stream of particles or a ray. Okay, so we've seen rays, hopefully in math, okay, and the source is where the ray comes from, and it travels in a straight line. Okay, so all electromagnetic waves travel in a straight line or a stream. Polarized light, when light goes through a filter, it eliminates some of those waves. These are very popular in sunglasses with polarized lenses, and so it blocks some of the waves because of the way the glasses are built. They're polarized lenses. What are electromagnetic waves? They are transverse waves that have some electrical and some magnetic properties, hence the word electro and magnetic. So the wave is moving in this direction, whoop, but the disturbance is going up and down. Okay, so it's not like our longitudinal wave. It's very much like a water wave. Why are electromagnetic waves so special? They consist of changing electrical and magnetic fields. Okay, so here's another picture showing us what the EM spectrum looks like and some of its uses. What does a transverse wave mean? Well, it just simply means that the disturbance is going up and down, and then the wave movement is going in a direction. Okay, transverse wave. What is the EM spectrum? The EM spectrum is a name for the range of electromagnetic waves placed in order of increasing frequency. Okay, so we have low frequency down here, and then higher frequency as we go up. Okay, and because of that, you see this relationship where you have increasing frequency and a decreasing wavelength. On the other hand, you have really long wavelength and low frequency. Okay, so that relationship is going to be very important in understanding the EM spectrum. Alright, so quick movie for you explaining some of the types of waves in the EM spectrum.
The electromagnetic spectrum, an immense scale used to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame and over 2,000 miles of tape. It is everything that the human eye can see. The importance of this frame is that the stars emit almost all of their light in this part of the spectrum.
And even though the light is visible, it still contains hidden tools. The secrets are in the spectrum itself. The visible light in this lamp comes from hydrogen gas excited by electricity to form a glowing plasma, similar to what happens in a nebula. By viewing the lamp through a diffraction grating, we can split the light up into 3 narrow lines on the spectrum, a virtual fingerprint of light, unique to hydrogen alone.
So in the spectrum, you see 3 features. One is red, one is a light blue, and the other is a deep blue. This pattern of wavelengths is absolutely unique to hydrogen. There's no way to confuse hydrogen in the spectrum with any other element.
Alright, crazy. I mean, the amount of light that we see is so small compared with everything else. It's pretty impressive. So on the low end of our frequency, we have radio waves, okay? And longer waves, longer wavelengths are used in TVs or phones, and then shorter wavelengths are used in search and rescue, police, military. Okay, so depending on the wavelength, radio waves are used for different things. Microwaves are the radio waves with the shortest wavelength and the highest frequency. So radio waves are also used in microwaves. So there are some of these radio waves that cross over into the microwave band. Infrared rays are the visible heat that you feel in infrared radiation. You can find infrared rays in sunlight, and as you can all of these waves, but you also might find them in like food warmers or ovens or whatever. Anything that has heat is going to be an infrared ray. Okay, so heat is the key ingredient there for infrared. Visible light are the only light waves that we can see, and visible light, we can only see this because the waves are moving just right, at the just right pace. The other waves are moving either too fast or too slow for our eyes to pick up, much like frequencies that are too high or too low. Okay, same thing happening with light. These are the frequencies we can see. And visible light is made of white light, and the white light is made of all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Okay, Roy G. Biv. We're going to come back to that over and over. So white light is made of all of those, red being the longest wavelength, violet being the shortest wavelength, which can give us an understanding of why the sky is the color that it is. Crazy. Ultraviolet light, these can be found in ultraviolet light bulbs. These can be found in any sanitizer, any sanitizing compartment. Sometimes we put goggles in an ultraviolet light case to kill all of the germs. EM waves with wavelengths just shorter than those of visible light are called UV rays. Ultraviolet rays have higher frequencies than visible light and carry more energy. That's important. That's why we need to put sunblock on, because these carry a large amount of energy. X-rays, we got Homer. Electromagnetic waves with wavelengths shorter than those of UV rays. These frequencies are just a little higher than UV rays. Because of their frequencies, X-rays carry more energy than UV rays and can penetrate most matter. But dense matter such as bone or lead absorbs X-rays and does not allow them to pass through. So because of the density of our bones, X-rays can go through almost everything in our body except for those bones, and that's why the bones show up on the X-ray. But that's also why we need to wear those lead-covered suits to protect ourselves from the high amount of energy. Then there's gamma rays. Okay, gamma rays are the shortest wavelength and the highest frequency. Because they have the highest amount of energy, gamma rays are the most penetrating of all the EM waves. These are the most dangerous. They can kill cancer cells, but they can also kill other cells. So pretty dangerous to be around, gamma rays. But again, all of these frequencies come from the sun. Gamma rays are mostly shielded by our ozone layer, which is lucky for us. In what ways are all electromagnetic waves the same? In what ways are they different? Well, they're all the same because they travel at the same speed in a vacuum. Remember, frequency does not have any bearing on speed. Okay, we learned that in our speed of sound lab. Frequency has no bearing on the speed of light either. But they all have different wavelengths and they have different frequencies. That's what's different about them. Okay, wavelength and frequencies. As wavelengths of EM waves decrease, what happens to their frequencies? Well, because the speed of EM waves is the same, as the wavelengths decrease, frequency increases. We learned that relationship in Goal 1. Okay, so this is really a review of that. Waves with the longest wavelengths have the lowest frequencies, and waves with the shortest wavelength have the highest frequencies. Okay, quick visual. Okay, and we can see that. High frequency, which would be this one, small wavelength. Low frequency, big wavelength. The amount of energy carried by an electromagnetic wave increases with frequency. The higher the frequency of the wave, the higher its energy. Alright, well that's it for this goal, and I've got an awesome song for you on the way out later. I mean, what would the world be like without auto-tune? Just imagine.
So listen up. Here we go. Electromagnetic spectrum. Here we go. Electromagnetic spectrum.
You know you want to dance. It's alright. It's alright. You can dance.